Good morning, dear students. Welcome to our session of microwave and antenna. So in the previous session, we discussed regarding the Smith chart and we had solved one of the problems. That is this problem what we have displayed over here, in which we identified what is the reflection coefficient at the terminal end of the transmission line. And we made use of a Smith chart for that. So now let us move ahead and discuss the next problem. So next problem is determine the length of the short circuited stub having characteristic impedance Z0 equal to 200 ohms and input impedance of minus J100 ohm using a Smith chart. So in this case, what parameters they have specified? They have given two parameters. One is the characteristic impedance of the line, which is 200 ohms, and the other parameter is the input impedance, which is sometimes denoted as Zin or sometimes denoted as Zs. Now, what is you have to do is you have to identify what is the length of the short circuited stub. So we have to identify the length. So in order to utilize this Smith chart, so what all parameters are there, we need to first normalize those things. So in this case, we need to normalize the input impedance. So that is Zn. So this Zn has to be divided with the characteristic impedance value for it to be normalized. So that is the first step what you have to look out. So when you normalize the input impedance, we obtain the value as minus j point 5. So therefore, if I just check out, the resistive component is 0 and the reactive component is minus 0.5. So that is what is specified over here. Now, if you just observe, this is what? This is the capacitive reactance value, since we are considering the impedance parameter. So what is the first step what you have to do? You have to normalize the value. So normalize the value. You need to locate these points, that is r is equal to 0 and x is equal to minus 0.5 on this Smith chart. So here, this is the chart. So here, when we observe, we need to identify which is r is equal to 0 circle and which is x equal to minus 0.5 circle. So in this case, if we just observe, so if I keep on moving, so it is 0.4, 0.3, 0.2, 0.1. So this outer circle which is there, right? This is actually associated with R is equal to, that is resistive component value equal to 0. Now, where is this line interacting with x equal to minus 0.5? So since it is minus 0.5, it is capacitive and I am using this Smith chart as a Z chart. So therefore, capacitive value will be in the lower half part, inductive values will be in the upper half part. So here we need to consider the capacitive, so it will be the lower half part what we'll be looking into. So on this, what we need to identify is we need to identify where is the reactance value equal to 0.5. So if you just observe here, this is 1.0, this is 0.9, 0.7, so on. When I continue, we can see that this line what you are observing is associated with the reactive component of minus zero point 0.5. So here what happens is these two lines, that is x equal to minus zero point 0.5 and r is equal to 0. So they interact at the point A. So this is the point wherein the input resistance is present or the input point is present. So that is what we have located. So we have located point A on the Smith chart where r is equal to 0 and x is equal to minus zero point 0.5. So that we have plotted now. Now we have obtained this. Now what we need to do is we need to identify the length of the short circuited stub. So now here one point to note down is the term which is specified as short circuit. So that is what we have to look out for. So I got to know where is the load, that is where is the input impedance. For example, so on the Smith chart, we have actually marked this ZS, which is nothing but the input impedance. So on the Smith chart, I have got this plot. Now what I need to do is I need to identify, it is given that it is a short circuit stub which is present. So I need to identify what is the length which is associated, what is the length which is associated with this stub. So in order to identify this thing, right, we need to move towards the load. We need to move towards the load by a length which is equal to some of the parameters. So this is just an example what they have taken. So on the Smith chart, we need to move a distance of L by lambda. That is what we have to look out for. So what is the next step we can look out is you can join the line OA and extend it up to the extreme end circle of the Smith chart to meet or the intersect the outer circle at A dash. So here what they have done is they have joined the center of the Smith chart, joined the center of the Smith chart and the point A, which is actually associated with the normalized input impedance value or the input point. So this line is joined and it is extended so that it intersects these outermost lines on the Smith chart. Now why that has to be done is as we remember in the previous case, right? If you just see what is specified over here, it is specified wavelength towards the generator. So this part readings which are there, right? They give you the wavelength towards the generator. And here we can see that this is wavelength towards the load. So these are the values what we get when we are moving towards the load. So now on the Smith chart, we have two cases. That is, one is associated with the open circuit and one is associated with the short circuit. Now in the problem here specified that it is a short circuited condition. So now on Smith chart, when you observe, right, when you observe, I get open circuit when R is tending to infinity and I get short circuit when R is tending to 0 or R is equal to 0. And as we know that R is equal to 0 is this circle. So here and R is equal to infinity when we come across, right, it will be a just smaller dot over here. So here this point gives you the open circuit condition and this point gives you the short circuit condition. So as specified, indirectly they have mentioned that the load is short circuited. The load is short circuited. So if that is the case, so this short circuited stub, what we are speaking, what is the length of this short circuited stub? So it is nothing but load is associated at this point and input is associated at this point. So this is nothing but it is giving you the generator end. It is giving you the generator end, and this is the point which is specifying the generator point. That is the input point. Now you know that load is short circuited. Now what happens is we need to identify the length which is associated with the stub. So now here what happens is on the Smith chart, if you just observe, I know load point is this and the generator point, that is the point A, is located over here, which is nothing but associated with the input impedance. So if I have to estimate the length, right, there are two ways. One, I specified you are moving towards the load. So that is one thing, that is, so from input end, you move towards the load. This is one. Or else, now in our case, what happened is we got to know that this is short circuit. So I know where is the short circuit point present on the Smith chart. So or else I move from the load towards the generator. In both the cases, you should be getting the same value. So here, there are two ways of looking at it. Now, if this is the input end, this is the generator end, I need to move towards the load. So if that is the case, you have to move in which direction? If you just observe here, if you want to move towards the load, so from this input point, you have to move in the anti-clockwise direction. And I know that the load is located at this point. So what I do is I keep on traversing till I reach the short circuit point, till I reach this point. So this is one way. So if you just see from this point, if you move in the anti-clockwise direction, you will be reaching this point. And if since you're moving towards the load, you need to consider this point. That is the scale. So, but what you will be doing is, if you just observe what is the length associated with that, you have to make some adjustments and take the reading over here. Otherwise, that is, if you just consider one entire circle on the Smith chart, right, it is equal to lambda by 2, which is actually 0.5. So 0.5 minus this length, this length, 0.5 minus this length gives you the length of the stub. So this is one way. Other way is in simple form, you know that this is the reference point where say the length L by W is equal to 0. And since we know that it is short circuit condition, I want to know the length. In order to identify the length, what I specified, so I can either move in this direction or from this point to this point. So now what I'm doing is I'll be considering this one. So in this case, so this is the load point, normalized load point. So from load point, I have to move towards the generator. So what is the direction I should follow? I should be following the clockwise direction. So once I follow this clockwise direction, I'll be following this clockwise direction. So when I follow that, I'll be reaching the input point at this location. So now I need to read what is this distance value. So how do I read it? I make use of the upper scale wavelength towards the generator. Now since this is 0, right, it will be 0, 0.1, sorry, 0.01, 0.02, so on I continue and I try to see what is the value over here. So you can see it is 0.42 and it is around, so it is in between 0.42 and 0.43. So somewhere it is around 0.425, somewhere around 0.425. So here from this point to this point, what is the distance? That is when I'm moving in the clockwise direction. That is what I have to estimate. So in this case, I'm getting the value around point, say 425 or 428. So that is what I have to look out for when I am identifying the length. So here, what did I get? So I got L by lambda is equal to around say 0.425, 426. So therefore, length is equal to 0.426 times lambda. So this is the length of the short circuited stub. So the same length will be obtained even if you're moving from this side to this side. But you should be careful that this is the input end. You have to move towards the load end. So in order to do that, you have to move in which direction? You can see that you have to move in the anti-clockwise direction. You start from this point, you keep on moving, and if you keep on measuring the distances, say from this point to this point, what is the distance? You keep on adding these values, you'll get to know it will be also equal to 0.426. So this is how we identify the length of the stub. So in this case, we obtained L by lambda is equal to 0.426. Therefore, length is equal to 0.426 times lambda. So this is how do you identify the length. Now, next the same problem what we can look out is determine the input impedance of a 200 ohm line, 3 by 8 lambda long, and it is terminated by a 100 ohm resistance. So I need to determine what is the input impedance using the Smith chart, the parameters which they have specified. If you just observe, that is impedance of the line is 200 ohm, which is actually the characteristic impedance, and he has specified that the line is 3 by 8 lambda long, 3 by 8 lambda long, and it is terminated with 100 ohm resistance. So this is nothing but the load resistance, which is 100 ohm. And this parameter what he has specified, right? This is actually length, which is 3 by 8 times lambda. So if I simplify it, it is 0.375 times lambda. So when I consider L by lambda, right, it will be 0.375. So this is what we'll be obtaining. Now what we need to identify is, we need to identify what is the input impedance and what is the reflection coefficient. So what's the first thing we have to do? Now we know what is the load value, that is ZL. The first thing what we have to do is we have to normalize this value by dividing ZL by Z0. So that is the first step what we have done. So ZL by Z0, this is the normalized impedance value. So when we simplify that, we obtain 0.5 plus J0. So we have resistance R, that is R is equal to 0.5, and the reactive components is equal to 0. So I'll write it as X. So it is equal to 0. So first we need to identify this point on the Smith chart. So here we have, I'll be referring to this part, Smith chart itself. Now we need to identify where is R is equal to 0.5. Where is R is equal to 0.5 plus J0. So here we can observe that. So if I refer this, so if I just refer to this one, right, you can see that 0.5, R is equal to 0.5 is over here, and say X is equal to 0, right? If you just observe this straight line which is there, this actually corresponds to X equal to 0. X equal to 0. So if you just observe here also we can see the values of the reactances. So this is 1.0, 0, 0.8, 0.6, 0.6, 0.4, 0.2, 0.1 and zero point 0. So this line corresponds to reactance value of 0. So we need to identify the interacting point of this X equal to 0 and resistance component equal to 0.5. So on the plot, right, this is the point which is associated with load point. So that is what they have pointed out. So here is the value, which is 0.5 plus J0, which is the load point. Now after this, what we need to look out for, what he has specified in the problem. Uh, he has specified the length. So I need to utilize this length, but this length is specified as 3 by 8 times lambda, so which is 0.375 lambda. So whenever we are using the Smith chart, right, all the values are normalized components. So length is normalized by dividing it with lambda. And if you're identifying some distance, right, it will be divided by lambda. So any value you obtain on this Smith chart, it will be a normalized value which is associated with these parameters. That is, if it is length, it will be divided with the wavelength, and if it is resistance or impedance, right, it will be divided by characteristic impedance. So now he has specified that the input impedance of the line is this much. Sorry, line is so we need to determine the input impedance. 3 by 8 lambda is the length of the line, and at that location I am having 100 ohm resistance. So it is indirectly giving us information telling that, is specifying that I have a ZL over here, and I need to identify what is the input impedance, but he tells that there is a load of 100 ohm present at a distance of 0.375 times lambda. So he has given you the information pertaining to the distance between the input impedance and the load impedance. So that is the parameter. So now what I have to do is, on Smith chart we marked the load point. We marked the load point that is corresponding to we mark the load point which is corresponding to point A on the Smith chart. So from point A, right, I have to move towards the generator by a distance of 0.375 times lambda. So at that point, I'll find the input impedance. So this is what I have to do now. So here, what we have, we obtain the load point. So from load point, I have to traverse a distance towards the generator. So if you just observe, if I have to move towards the generator, I have to move in the clockwise direction. So from this load point, I'll traverse a distance of 0.375. So if this is 0, if this is 0, I have to traverse a distance of 0.375 from this point. So I have to traverse that much distance. So in this case, where is that value falling? So if you just observe in this chart, so if you just observe where is that point falling. So if I move in the clockwise direction, I have to make use of the upper scale. So this is 0.37, 0.375 is somewhere here. So this point is being shown over here. Okay. So this is, I guess this is 0.375, this is 0.38, sorry, this is 0.3738, this is 0.375. So what we have done on this outer circle, we started from the load point, and we traversed a distance of 0.375. So I got to know that that point is here. Say we'll specify it as B dash. Now what we have to do is, we need to join B dash and O. We need to join these 2 points. So once we have joined this, there is another one thing what we have to do is, we had identified the load point. So we have to consider a radius of OA and draw the VSWR circle. We have to draw the VSWR circle. Now this VSWR circle and this line OB dash are intersecting at one point, which is marked as A dash over here, which is marked as A dash. So this value which is there is nothing but the input impedance point. So if I read out the read out the impedance value which is associated with this, it will give me the input impedance in normalized form. So if I just read out this value, so I'll just try to check out what is the value. So here, this is the circle with which it is associated, a resistance circle. So resistance circle is roughly around, so if I just check, I'm not able to read on this. So I think it is around 0.7 over here. So I have to read what is the resistive circle value. So this one, and what is the reactance circle value. So that will give me the value. And since this point is located in lower half, and we are using this chart as a Z chart, so the reactance value will be actually negative. So in this region, so it is around point, 0.7 plus minus j 0.5. So if I just read out, this is the value what I am getting. So here let us just check that case. So yes, we are getting it around 0.8. Sorry, the line is 0.8. this line is, this resistance circle is around 0.8. It is 1.0, 0.9, 0.8 plus, so let's check out, plus 0.6. So this is the input impedance in normalized form. So now if I have to get the original impedance right, we have to multiply this normalized resistance with Z0. So when we multiply it, we are getting the value of 160 minus J120. So remember in this case, why we are specifying minus. So in the Smith chart, you can just see that point A dash is located in lower half of the Smith chart. So wherein it is capacitive. And since we are using this as a Z chart, right, the capacitive values are identified by a negative. So that is what we have shown over here. So it is 160 minus J 120 ohm. So this is how you identify the input impedance. So again, in simple form, if I just specify, first locate the normalized load point, draw the VSWR circle with center as the center of the Smith chart and radius equal to OA over here. Once you do that, you traverse a distance from the load point, and the distance should be equal to the parameter L by lambda, that is 0.375. So, and from that point, you join the line, such that this line and the VSWR circle interact at one point. So when they intersect each other, you will be able to identify what is the input impedance. Now there is another thing what we have to identify, what is the reflection coefficient. So so this is how you identify a reflection coefficient is pending. So here there are two ways. So you have drawn the VSWR circle. So project one end, that is on the horizontal line, this VSWR is cut by the VSWR circle by at 2 points. So just check out where the reflection coefficient parameter is specified on the Smith chart. So what you have to do is you have to project the one end of this VSWR circle onto that scale. So, and that scale will be cut at one of the points. So in this case, it will be, say, they have specified it as A. So the here, that point, when you read it, right, you will be able to obtain what is the reflection coefficient's magnitude of the reflection coefficient. So here another point to note down, if you want the angle, right? So if you want to identify the angle associated with the reflection coefficient at load end, you need to extend the point OA dash. You need to extend this line OA so that it interacts at the outer circle. So wherein you will be having the reflection coefficient angles. But if you want to identify what is the reflection coefficient at the input end, what you have to do is you have to extend the point OA dash such that it goes and intersects the outermost circle where reflection coefficient angle is specified. So that will give you the information pertaining to the angle. So here I'm getting the magnitude, and on this circle, right, I'm getting the information which is associated with the reflection coefficient. So these are a few of the problems what we have discussed